I think we've exhausted all of the possibilities of things that can happen with the first derivative. Now let's take a look at the second derivative and a topic referred to as concavity. Now, we know that from the first derivative, if we can draw just a rough sketch of a graph, going anywhere we can tell what the tangent line is going to look like, because now we've grown used to seeing how tangent lines go along curves. So like along this curve, if you take any point on the curve and you were to create the tangent line from that point, you would see it has a negative slope, which means that the graph is decreasing. And then by the time you get here where it's horizontal, the slope is 0. You know to look for zeros of the derivative. And then along here you can see that the graph is increasing. We draw a thicker tangent line so we can see it perhaps. It's hard to see that. But now positive slopes indicate increasing, negative slopes indicate decreasing, and zero slope indicates, I guess you'd call this saming. So we can see decreasing, flattening out, increasing, flattening out, decreasing, flattening out, then increasing. In fact, we made those sign charts to keep track of where the first derivative was positive or negative. So in a way, we could think about these lines as being direction arrows, if you will. They kind of tell us how this curve is going. Like if I get to this point here, if this were somehow attached to a string and then you suddenly let the string go, you get the idea of flying off on a tangent. That's exactly what would happen if we thought of this as being an object that is moving in 2 dimensions like this. And at any particular point, the derivative is telling you what it's doing as far as where it's headed. Now the second derivative is going to be concerned more with curviness than straight lines. So I'll give you an indication what I mean. If you have a function, say a linear function, one that looks like mx plus b, and then you take the second derivative, that's going to equal 0. Well, what that means is that this straight line exhibits no curving behavior. So the second derivative tells us 0 information about the curve. However, if we move up a degree and go to a second degree polynomial, anything like this, ax squared plus bx plus c, the second derivative is going to equal 2a. Now that's a constant, that's true, but it does tell us that it has some curviness to it. And everybody knows it has some curviness because it's a quadratic. Let me show you. I have, in my GeoGebra program, I have graphed a curve here. It looks like y equals 3 times x minus 2 squared. And what I'm doing here is along this line, I'm having it graph the tangent line for any point on that curve. So you can see how the tangent line is getting steeper and steeper and steeper as it goes up the curve. But as it comes down the curve, you can see that it becomes less steep, less steep, less steep, less steep, until, let me see if I can pause it there. You can see that it wants to be 0 right there at the bottom, horizontal line, and then it will start having a positive slope because the graph is now increasing. What I want you to notice, though, is that at any time or any point, the curve itself lays on top of the tangent line. Do you notice that? Throughout the entire curve, the tangent line is always below the graph. And this graph here is one that you would say opens up. Well, we describe this as concave up. So a graph like this is concave up because, well, it opens up. If you want to think of it that way, that's fine. But mathematically, the reason is because it lays atop any of its tangent lines. What that means is if the tangent line represents a constant velocity, then a curve represents a velocity that is changing. In other words, it's undergoing some acceleration. So it's able to accelerate away from the straight line that represents the tangent point, the tangent line. So let's write a couple of these details down. Notice that was a quadratic. So in fact, the quadratic that I had over there was 3 times x minus 2 squared. If I take the second derivative, I'm going to get, well, remember, bring the 2 down to make that into a 6. I'm going to do the derivative of x minus 2 is equal to 1. All right. If I simplify, I get 6x minus 12, or multiply through, whatever you want to call it. When I take the next derivative, then, I get 6. So for the entire time, no matter what x is, the concavity is a 6. That means it's curving, since this isn't 0. You have 2 types of concavity. We have concave up and then concave down. Now, usually when you were graphing quadratics before this course, they may have told you to look at the leading coefficient to determine if you were going to have it open up or open down. And that's true, because the leading coefficient has the same sign as 2a does. That means if 2a is positive, you open up. If 2a is negative, you open down. It almost seems like concavity was invented to describe quadratics, but we use it for a little bit more than that. We use it to describe more subtle details on a curve. Let me show you what I mean. Okay, now I'm graphing a curve. Here you can see what it is. G of x equals 3 times x minus 2 cubed plus 1. I have it doing the same thing as before. I've got at each point on the curve, I'm able to move this to show me how the tangent lines go. So look here. Let me stay down here for a minute. Do you see this? If you look, all these tangent lines happen to have positive slope, but that's not the important thing. Notice this. The tangent lines are above the graph until I get to 2. Right at 2, if I can stop it, it's flattened out. But then after 2, look what happens. It now goes up. Now, remember when we were finding increasing and decreasing, we had increasing, we had a 0 for a derivative, but then we were increasing. So we're increasing, 0, increasing. That particular point gave us no new information about the graph because it wasn't changing signs as you went before and after this particular point. Well, here though, in the second derivative, there's a lot of difference you can see. The tangent line is on top of the graph until I get to the flat point. But then now look, as I move forward, move to the right, now the tangent line is always below the graph. So it changes. Let's go back here. Here we have concave down, 0, but then concave up, concave up, concave up. So this point right here is an important point in this world. 2, 1 would be referred to as a point of inflection. We consider the graph to be concave downward for all x values up until we get to x equal to 2. After that, it's concave upward. Here's the curve. We have, let me call it f of x equals 3 times x minus 2 cubed plus 1. And as I was indicating, it's concave down until you get to 2. So concave down. On negative infinity to 2. So I list the x values for this. And then concave up on 2 to infinity. And the point 2, 1 is an inflection point. That's where concavity changes. The x value is the place where it changes from concave. Well, you'll get second derivatives will be negative where it's concave down and positive where it's concave up. I'll show you. We do something just like we did. If I didn't have this graph in front of me and I were stuck with doing this by hand, let me take f prime. And I'm going to use the chain rule, of course. So this 3 comes down front. And I have 9 times x minus 2 squared. The derivative of x minus 2 is 1. So that doesn't change anything. Then f prime prime. That equals 18 times x minus 2. Now, what we do is we set this equal to 0 like we did before. 18 times x minus 2 equals 0. This implies that x equals 2. So there's only one location where there's a 0 for the second derivative. Draw a line, number line. And this will be my f double prime number line. I'll mark off 2. And as I did with the first derivative, I'm going to try a test point for it. Before 2, and a test point after 2. So before 2, I guess 0 would be the easiest thing to try. I'll plug x 0 in for x, and I end up with negative 36. So if I plug in 0, I get a negative number, so it'll be concave down. And that, of course, we see this based on the graph, based on what I'm telling you. Concave down where the second derivative is negative. And then I'll pick a number over here. I don't care. 3 is fine with me. If I plug x equals 3 into here, f double prime of 3 equals 18, which is positive. And I'll draw a symbol like this to indicate concave up. And these do exactly what I was indicating here. 2 is that special place. X equals 2 is the special place where it changes concavity from negative to positive. Let me just do a quick example. We'll check the graph later on, but for now, determine, you'll see questions something like this, determine the concavity of, and I'll stick with some sort of a cubic. I have not thought of this before, but we'll do x cubed plus 3x squared minus 7x plus 4. And so all I care about is concavity. If I worried about increasing and decreasing, it would be the first derivative. But I'm just going to go right through the first derivative to get to the second derivative. I didn't mean that I'm going to take the second. You've got to do the first derivative before you can do the second derivative. So I'll have 3x squared plus 6x minus 7 will be the first derivative. Take the second derivative, and I get 6x plus 6. And let's set that equal to 0. Well, I can factor out a 6. 6 times x plus 1 equals 0. So that tells me that x equals negative 1. So now let me check the concavity without actually looking at the graph. All right, give me a number to plug in before -1. I guess -2 seems easy enough. -2. If I plug -2 in for x, I get -12 plus 6 is -6. It's negative, so we have concave down. Pick a number bigger than -1, I'll pick 0. Plug x equals 0 into f double prime, and you'll get 6, which is positive, concave up. So, we're concave down. On -infinity to -1, concave up on -1 to infinity. And that means the point -1 comma something is going to be a point of inflection since it changes from negative to positive there. So what is, I need to have the y value when x is -1. When x is -1, I'll plug it into here. So let's go ahead and copy this and throw it in. Let's see, f of -1 equals -1 cubed plus 3 times -1 squared minus 7 times -1 plus 4. That equals -1 plus 3 plus 7 plus 4. That equals 10 for 13. So the point -1 comma 13 is a point of inflection. In my mind, if you think of this from a physics connotation, or I mean, actually the calculus was invented to try to study physics, so this makes sense. In my mind, when the curve is concave down, I think of deceleration. The tangent lines are becoming less steep as you come up to the point. So you can think of the velocities as getting slower and slower and slower until they get to 0. On the other side of it, it'll start at 0, but then increase and increase and increase, meaning that now you're accelerating. So if you were in a car and this kind of stuff was happening, you could think of putting on the brakes until we came to a stop, and then accelerating again thereafter. So let's just look at a few situations that can happen here. We're going to go hardcore next video with very serious graphs, where we try to uncover as much detail as we can. So let's take a look at some of the things that can happen. Like we just had, you could have something like this that goes from concave down to concave up. That's the thing we just did. Or of course, this could be reversed, and it could be like this, so it could start concave up and then come concave down. You could do something like this. These are strange ones, like something like inverse tangent looks like this. So hopefully you can see that it feels concave up here, then somewhere around here is a point of inflection, and then it's concave down. So you're going from positive to negative for the second derivative. You could have something like this. That kind of a graph would go from concave down, point, whatever you'd call this point, critical point, then concave down thereafter. You would not count this as an inflection point here. Not an inflection point. The reason why is the concavity doesn't change before and after that point. The concavity goes from, negative to negative, from negative to negative. So, although this point would be a point of interest, it wouldn't do anything for us. As an example, let's do f of x equals arctangent of x. Now when I take its derivative, that equals 1 over 1 plus x squared. And then the second derivative, I'm going to use the quotient rule. So I'll take the derivative of 1, the numerator, I'll get 0 times, leave the denominator alone, 1 plus x squared, minus, now leave the numerator alone, but take the derivative of the 1 plus x squared. And that'll be all over 1 plus x squared squared. The numerator then becomes negative 2x, and the denominator is 1 plus x squared squared. Now I can tell the derivative the 0 for this thing happens when x is equal to 0. This does not have a 0 down here, so there's no critical values gained in the denominator. Just in the numerator, the only 0 happens when x equals 0. Before x is 0, let's say pick a point, say negative 1 as a test point. Plug it in, I'll get positive 2 over some positive number. Notice you're always going to get a positive number in the denominator. So, this will be positive. We're going to be concave up until I get to 0. And then if I test something over here, I don't know, 1, I'm going to get a negative number, so it'll be concave down. And this is the graph I was sort of indicating it was. Right here, concave up until you get to 0, then concave down thereafter. So the point 0, 0 happens to be an inflection point there. Now something that exhibits this type of behavior is something like f of x equals x to the 2/3. Let's take the first and second derivatives of that. F prime of x equals 2/3 x to the negative 1/3, and then f double prime of x equals negative 2/9 x to the negative 4/3. Now, since you have a negative exponent here, 0 is a critical number, except the thing is not defined when x equals 0. So I typically write something like this. I'll put a hole there to indicate that I can't actually plug 0 in. All right, let's plug a number in before and after 0. Let's say negative 1 before and positive 1 thereafter. If you plug in negative 1, well, when you take negative 1 to the negative 4th power, it becomes positive 1. The cube root of positive 1 is positive. What I'm getting at is you get a negative number. And since it's an even exponent, well, at least the 4 is even, you also get a negative over here at 1. So it's concave down followed by concave down. So that exhibits the behavior that I indicated here, where it has a sharp point, but it's not an inflection point. So there's no inflection point for this particular graph because it goes from negative concavity to negative concavity. You cannot have an inflection point that is a hole either. That should seem pretty obvious. There's no point there that you could have. And these are fairly indicative of the situations you could have. Let me do one more, I think, that'll be beneficial is f of x equals sine of x, and f prime of x equals cosine of x, and f double prime of x equals negative sine of x. Now, if I were interested, say, on the interval from 0 to 2 pi, let's say I go from 0 all the way to 2 pi, so one complete period. Well, where is sine, negative sine, equal to 0? Well, it's equal to 0 when at 0, pi, and 2 pi. So these are critical numbers. And then let's put numbers in between here. Probably the easiest thing to do would be to put a pi over 2 here and then 3 pi over 2 here. Okay, and then plug them in. If I plug pi over 2 into f double prime, I'll get -1. So it'll be concave down. If I plug 3 pi over 2 into the second derivative, I'll get negative of -1, which will be positive and will be concave up. So the graph of sine goes like this. It comes up, as everybody knows, and then hits the graph, then below it, and comes back up. Well, what I'm indicating here is that we have an inflection point here right at pi. It's going from concave down, negative, to concave up. So, and cosine will be a similar thing. They're the same kind of graphs, so they're shifted from each other.